I lost my internet signal momentarily. Can you hear me?
Yes.
Okay, thank you. Let me share the screen here. Saving. Okay, so you got up to here, right? That you got, and then I was working on the phasor diagrams. Okay, the phasor diagram rotates in the XY space, in this XY space. And now what I can do, I'm going to write down the phasor for the current. Strange. Let's see if I can get it. The phasor for the current itself. Looks just like that. Okay. And now I can, let's see, do I have a group? No. Group. I'm going to eliminate this one, and I'm going to rotate this one. Here we go. V naught. I gotta put the I naught there. I don't have I naught. Oh, I do have I naught here. Okay. Next frame. Here's my next frame. Rotate. Okay. Delta I V naught, and I gotta put, I'll put in the next frame. I'm gonna put it, here we go. Rotate. And now you have this animation, right? A given instant of time, V naught, delta I, delta T, and I naught are here. And then move here, rotate here, and so on. And I still have to put the I naught. Gotta label it. Here's labeled. Here's labeled. Next. Here's labeled. Next. And I'm going to label here as well. Okay, so here you go. First frame, second frame, and so on. We don't need that anymore. Let's see. Okay, and now let's see how I'm gonna do here. I'm gonna do like that. Okay. Now, before. Why did I have total? In a AC circuit. Let me see what's going on here. Yeah, inductance. Okay. AC circuit with an inductor. An AC circuit with an inductor. Okay. And Let's see what's coming next here. Okay. Okay, so stop it here, right? And let me write down, did I write down the equation for the current already? Not yet. The equation for the current is going to be mathematical solution for the equation of the current requires advanced calculus. So I will just write down its solution, right? Its solution. The final result. Write down the final result. Okay, that's how it looks like. Lag. This negative here means that the current is lagging the voltage in the circuit. Then and here you go. Here's the voltage, the equation for the voltage in the circuit. Here's the equation for the current in the circuit. Notice that we have a V naught 2 pi F additional term. We have this additional term here, 2 pi F, downstairs. Okay, and now we can continue with our table. The table that I started out there, right? So here we go. I'm even going to here we go current. Here is going, instead of putting I naught, I'm gonna put V naught over R. Oops. Here you go. V naught over R. Instead of putting I naught, I'm going to put V naught. What did you get there before? Let's take a look here. For the capacitance, right? V naught over this thing here, right? 2 pi FC or C 2 pi F. Like that. I prefer to put this term right in here. Okay. Good. 1 divided 2 pi FC is this term right in here. And then the I naught is going to be V naught over 2 pi F L. 2 pi F L, like that. And the reactance, inductive reactance term is going to be like that, depending on the frequency of the circuit. They all here have units of resistance. Okay, RLC. I'm going to copy that and duplicate it downstairs. Okay, then don't forget the negative sign means that the current lags the voltage. The current lags the voltage. Yeah. Okay, so one more student coming. So the voltage of the generator. Don't forget, we are talking about the voltage of the generator, right? So we go. Current for AC circuit with a capacitor leads, with a resistor is in phase, with an inductor lags the voltage. In phase with, right? Lags the voltage of the generator. What becomes a little bit more difficult is we can also say now on the other way. We can also talk, instead of saying that the current leads is in phase and lags the generator, we can go the other way. The voltage, okay, of the generator with a capacitor. Now we're taking the reference with respect to the current. Okay? If the current leads the voltage in the generator, whenever you have a capacitor there in the circuit, we can say the opposite as well. We can say that the voltage lags the current in a circuit that has a capacitor. Okay? And the same would be applying to the inductor. And now I can here write my equations in terms of the current. Okay, so here we go. I'm going to repeat what I got there. Okay, so here we go. Voltage for an AC circuit with a capacitor. No, let's see here. I didn't copy it. Okay, so here you go. So we're, like I said, we were taking. I have to rewrite it here. Let me. I already rewrote it here, right? Let me see if I have it. Let's see here. I thought I had seen. Yeah, what I'm going to do the following, right? I'm going to rewrite it outside the table so you understand the steps that takes to the next spot, okay? This one I'm just repeating. So here you go. Generator. Current or the resistor. Side by side. One next to each other, right? Current of the capacitor in an AC circuit. And then current. Oh, here should be inductor, I sub L. Nope. I sub L. So all those equations for the current are taken in relation to the voltage. Okay, let me write that down. All the above equations of the phase of the circuit are taken with respect to the voltage of the generator. Okay? However, in real life, what stays constant, however, in real life, you must take the voltage with respect to the current. And there's a reason for that. With respect to the current, okay? Or, no, I'm going to write that down. Here you go. Like that. Here's going to be the current of the circuit. I naught sine 2 pi ft. And here is going to be the voltage of the circuit with a resistor. Okay? Here is the voltage of the circuit having a capacitor. And that also is going to be something like that. But it will have to lag, right? Because the current leads the voltage. Now the voltage must lag the current. And we do the same for the inductor. We get a V naught here as well. Oops. And we must lead. In this case, leads in phase, No, in phase is the other one. This one lags. In phase, like that. In phase with the current. And we are going to need exactly those three equations for the next thing that we are going to do. Okay? The next thing we are going to do is what happens. The next thing we will do is to determine what happens when we put all these three elements together in a single circuit. The RLC circuit, we call it. Oh, LCR, whatever you want to call it. The book gives a different name, right? Let's see what the name the book gives to the circuit. Wiley plus. Let's get there. Okay, we still have 20 minutes to go, right? Let's see here. Launch. And yeah, that's the capacitance. Capacitor. No, there's a resistance, right? Let's see here. Here go the vectors, the phasors, inductors, and inductive reactance. We covered that. Circuits, now that's what we're going to do. RCL, we call it RCL, RLC. You know, we call RCL, some books call it RLC. What happens when we put all those three together in the same circuit? And that's what we're doing right now. That's what we're going to do right now, okay? That's a good drawing. And apply first step. I'm gonna copy and paste to my, okay. RLC, here, RLC, right? I'm calling that RLC. The book called RCL. The book called use circuit RCL. Okay? Applying Kirchhoff's loop law. Applying Kirchhoff's loop law, right? And that would be the example. Okay? In this circuit, it's very important. Why are we doing that with respect to the current? There's a very good reason why we're doing that with respect to the current. And the reason is that the current must have a continuity throughout the whole circuit. You cannot have one current that has one phase for the resistance and another current that has another phase for the inductor. You cannot have it, okay? Because the current is something that flows through a single point here in this circuit. That's why I came up with that other equation. But the voltage, you can have a discontinuity in the voltage because the voltage pertains to a single element in the circuit. Here, V sub C, here is going to be V sub L, here is going to be V sub R. But the current, no, the current must be the same throughout the whole circuit, okay? Since the current must be the same throughout the whole circuit, coming. Since the current must be the same throughout the whole circuit, okay, comma, we must have the following relation, the following equality. And I'm going to copy this one here. Nope. This one here, let's copy it again. You didn't get it. The first one. Okay, let's see if we get it now. Yeah, it does. I sub R must be equal to I sub C, which must be equal to I sub L. And this one, I'm going to call it the current of the RLC circuit. And you don't need that. Okay. Even better, I'm going to simplify the notation. I'm going to just call it I. Okay. It must be the same because those elements are in series. Okay, those elements are in series. If they were not in series, then it would be a different story. It would be a different story. And now we are prepared. Here you go. I'm going to copy and paste this thing here. Another way of saying the same thing. In this type of circuit, you cannot have a discontinuity in the circuit through each element. In other words, the phase of the current through the resistor must be the same through the inductor and the capacitor. For this reason, comma, we must always think of the phase difference with respect to the current. With respect to the current. The discontinuity instead lies on the voltage, which is let's see how I'm going to put that in words. Inherent, right? Inherent for each element of the circuit. It's okay to have different phases for the voltage, but it's not okay to have, but for the current, you must have the same phase. In other words, right? In other words, it is okay to have different phases for the voltage, but the current must have the same phase throughout every element in the circuit. Okay? And now we are going to solve, right? Another example, I'm going to call that example 4. Consider RLC AC circuit with known R, C, L, and frequency F values. Use the Kirchhoff loop law to find an equation for this new AC circuit. Okay, so that's not difficult, right? So item A, using Kirchhoff loop law, the resistor, in the direction of the current, the voltage of the resistor is going to drop, okay? In the direction of the current. And for the capacitor, okay, you have to have the proper sign. Here you go. How does it work? Let's see here. Let's see if I have the right. If at a given instant of time, this pole here of the generator is negative and this one is positive, it means that this plate here of the capacitor is going to be positive, okay? So when we transverse from this positive polarity to the negative polarity, we are going to lose electric potential energy. Let me see if I have it here. This one here, doesn't look like I have it. Okay, I'm going to put the positive signs right here. If at a given instant of time, the polarity here is positive and the polarity here is negative, it means that the capacitor must have a positive polarity on the right side of the plate. Okay. Yeah, it doesn't want to do what I want. I'm just gonna copy and paste on the other side. And here must be a negative polarity. Negative, negative, ooh. Negative and negative. Okay. That's why we have a negative sign in the voltage of the generator, of the capacitor. That's why we have a negative sign here. And now we can continue with our derivation, right? Now we have to substitute each of those terms that you see right in here. For the generator, we already have this term. For the capacitance, we have this term. For the resistor, we have this term. And for the inductor, we have this term here. And we get what it was asked to do in item A. Just the equation of Kirchhoff loop law. That's the one. Q sub C over C. And let's not forget, this one's going to be a function of T as well, right? This is going to be a function of T, and the current is going to be a function of T. Current is going to be a function of T. What do you want to do next? use a phasor diagram to find the net voltage of the circuit, RLC. Okay? And now we are taking the voltage with respect to the current. Here is my I naught that's rotating in this XY space. Okay? The voltage of the resistor is in phase with the current. The voltage of the capacitor lags the current. The voltage of the inductor leads the current. And we combine all those three phasors, we get something like that. Okay. Don't forget, this whole set is rotating, right? Don't forget that. Is in phase, the current is in phase with the voltage of the resistor. It's the current leads the voltage of the capacitor. The current lags the voltage of the inductor. And now we are going to use this diagram to find the net voltage of my system. The first thing we do, what's easier? Notice that the voltage of the capacitor, the thing acts just like a vector, okay? This phasor diagram works just like a vector in the XY space. Consequently, this big length here of VL is being canceled by this VC because they are off phase by 180 degrees. And that's what you have, VL minus VC. And then we gotta sum up vectorially the VLC with the VR. Okay? You go. And that's the VLRC. What you see here is the VLRC. VRLC. Okay? And then we do have this phase difference between the net voltage through the system and the current. Okay? Here you go. The phase difference is this phi right in here. There's this phi right in here. This phase difference is kept constant through time. And now we can rewrite our current equation for the current. Let's write that down. We go. The current passing through all the elements must have the same phase. We cannot have a discontinuity. Use a phasor diagram. I gotta do item B, right? Use a phasor diagram to find the net voltage of the circuit. Let's do it here. Item B. Item B, I gotta copy and paste, and then I'll write the item C soon. Item A. That's item B. Item B, like that. The first diagram. The second diagram that you saw. And the third final diagram. Nope, not final yet. Gonna have it final soon. Here you go. Summing VLC with VR. Summing VLC with VR. This VR. Okay, the net voltage. I'm gonna put it here. The net voltage in our LC circuit should be the vectorial summation of all voltage, of all voltage phasors. This is the current final. This is the final phasor diagram having an angle difference with the current phasor, with the phasor of the current. And now what VRLC is gonna be? Okay, VRLC is going to be written in the following way. Here you go. The VLC and VR makes an angle of 90 degrees, right? I'm even going to rewrite the VLC in the terms that you already know how it is. Here you go. Like that. V sub L minus V sub C, right? Because they are 180 degrees off. Because they are 180 degrees according to the diagram. But then I can rewrite that in terms of the reactance. The reactance is going to X sub L times the current, X sub C, V equal Ri. I'm using just the equation for Ohm's law. The V sub R is going to be Ri raised to the second power. Here you go. Here are the common terms, right? I, and I. The common terms are in reality is I squared. Okay, I'm gonna put I squared here outside. And I can cancel I can cancel I. And this I is gonna be, let's see here. I'm gonna put everything already, like R squared, I squared. Common term is the I squared. Because the I squared is a common term, I can take it out of the square root. And we are left with this term. Here's going to be the total reactance. Okay, total reactance. And I call it Z. Books usually call it the parameter Z. Okay? It's still Ohm's law. V equal to RC. Okay? And that it was item B. Is to find the net voltage of the circuit. That's the VRLC. And we can even write it down, right, as being, I'm gonna put it like this term here. Multiply it by I naught two pi F 2 pi FT, like that. Oh, by the way, we still have a phase term, right? The phase term is this phi angle here. So voltage leads the current. or the current lags the voltage. Now, what about item C? Let's see item C here. Write the current for this circuit, right? If you write the current, I'll say item C. And by the way, this apply whenever, okay? The above apply whenever V sub L is greater than V sub C, okay? If it were the opposite, then the phi angle would be negative. So we can here write our item C. Okay. Another way of writing the whole thing, right? That would be in terms of the voltage, right? If we consider the voltage as being V naught with no phase right in here, then the current would be written as though it lags the voltage. And what about the angle phi? You can find out what the angle phi is just by looking at the drawings there, right? At the go. Okay, go back to this guy right here. We're gonna go on our break very soon. Okay, the net. Let's see here. Yeah, in order to see that, we gotta get the other ones here, right? Let me see if I can superimpose everything. Yeah, I need this one here in order to get the angle phi. Let's take a look. Snipping tool. Let's get my snipping tool here. Copy. Copy only. In order to get the angle phi, here you go. Here you go, like that. Look here, we have a right angle triangle right here. Okay? So, let's see. Tangent of phi is going to be VL minus VC over VR. Okay? That was the tangent of phi. Okay, item D, looking at the above diagram. Looking at the above phasor diagram, we can obtain the angle phi in the following way. Here go. Tangent of phi is VL minus VC over VR. We can go and move further. VL is IXL minus IXC divided by IR. I cancels out. And then we spell out X sub L and X sub C, just like we saw before. Okay, so that's the advantage of using the phasor diagram. You can solve it just using geometric arguments. And then phi is going to be arctangent of that. Wow, that's 10:50, right? Yeah, we're about to. Any questions about that? We're gonna have our break from 10:50 a.m. to 11:05 a.m. Let me see if I'm missing any questions from you in the chat. No, doesn't look like. Okay. So I see you in 50 minutes, right? Bye-bye. See you soon. I'm back here, and I'm going to share the screen with you. So that's how we calculate the voltage through a circuit, an AC circuit that has a resistor, an inductor, and a capacitor as their elements. And now we're going to talk about power in an AC circuit. And we're going to follow the same steps that we did for a DC circuit, okay? And the power, is given by Ohm's law. Is a P equal to VI. Just like we had for a DC circuit, you're going to have that the power in an AC circuit is going to be also VI. And this power is Ri can be rewritten as Ri squared using Ohm's law or V squared over R. Okay. So in the DC circuit, this power is constant because the voltage and the current, they do not change as time goes by. The instantaneous power is constant because V and I are constant. Okay? While in the AC circuit, the power must vary because V and I, they vary with time. Must vary in time because V and I are a function of time as well. For this reason, we must define an average power, but it must be a special type of average for the following reason. Must be a special type of average, okay? Special, let me put it here in italics. Oops, gosh. Okay, type of average for the following reason, okay? Let's start with the generator. I don't think I talked about that before, right? This is a special type of average. Let's start with the average, with the generator. That's the voltage of the generator, right? V naught sine 2 pi ft. If you take the average of the above function, okay? If you take the average of the average in time, we're taking the average in time of the above function, comma, over a single period, right? Of the averaging time over a single period of the above function, comma, we will get 0, right? The time that the time that the sign is spent in the positive region is going to be not the amount. The amount in the positive region is going to be canceled out by the amount in the negative region. Okay? That's why we have to consider a different type of average. We don't want a 0 result for this average. For this reason, this average, this regular average, for this reason, the regular average is not very useful. And we must define a special type of average. And we must define a special type of average that we call the root mean square value, or the square root of the average of the squares. Root mean square value, RMS of this, or the square root of the average of the square. Okay, so what exactly do we do, right? In this special type of average, we do the following. To get this special type of average, comma, we do the following. First, we square the original value to eliminate the negatives from the equation. And what I mean by square, exactly what we do. We square this equation right in here. Okay, here we go. This one and the sign. Next, we take the average value of this square. Next, we take the average value of this square. And I'm going to put it right in here. Up. Not all what. Here we go. Next, take the average value of this square. And finally, we take the square root of the above average. Okay? So I'm going to represent the average of the square value by a pointed bracket like that. Let's see here. Like this one. Okay. This one is a constant. So the average of a constant is going to be the constant itself. Okay. So I don't have to we take this. That's the symbol for the average, the pointed bracket, the triangular bracket, whatever you call it. And finally, we take the square root of the above average. That's the root mean square value, a special type of average that's used with frequency in engineering and physics. Okay? When I take the square root of this V naught square, it becomes V naught. And then when we take the square root, you're gonna see what we're gonna get when we take the square root of this other value. Okay, so here you go. Let's visualize how it looks like. We start with something like that. Let's visualize, let us visualize in a graphical format. Let us visualize in a graphical form how this calculation is done. Okay. We start with the voltage. Here's a full period. Here is V versus T. And here's a full period. If I take the average of this curve here over a full period, we're going to get 0. Okay? So what we have to do again, first we have to square it. Okay, so notice from the above graph that, this area here, sum to this area here is going to be equal to 0. And that was the average is. The average is related to the square below, to the area below this area, below this curve. Okay. So when we square, let's see if I can get it. I don't have it. I'm gonna show you how it looks like. I'm gonna plot it from 0. Now roster. Let's get that. Roster. It's moving approximately. Is that the one? No, that's not the one I want. This one that I want. Okay, so let's use this, this one here, right? And now when I square this equation, it's going to look like the following. Whoa. I don't like it's too large. Well, I'll plot it separately. Yeah, let me plot that separately. Insert. Okay, that's how it looks like, the square. Right? It's gonna be positive everywhere. It's still like a sine wave, right? But it's shifted upwards. And also the frequency increased. The period decreased by half, right? See? And consequently, the period. Let me do the following. I'm gonna plot this one right in here. Yeah, I'm gonna do that. I'm gonna superimpose them so you can see them more better, right? Here you go. And there's a way of doing that without, here you go. Add, let's see, select data. Let's see, that's the one. I wanna add this one, just like we did before, right? Squared value, X is gonna be this one. And the Y value is going to be this one. Here you go. There's a little trick that I'm going to do it. You're going to see what I mean. Another student coming. Oh, what happened here? Huh. Something odd happened. Let's see. Something really odd happened. Let's try it again. Select data, add X values. Here you go. Voltage. And then this one here. Let's see what happened, why it didn't plot properly. I think it's gonna plot now. That's odd. Huh. Okay, so I did everything I could have done, right? Okay, just try to visualize what's happening here in the graph, right? Here you go. For some reason, I cannot add the other one. I do not know why. But here you go. Right in here. Okay, the value here is 1.6, right? 1.6 at t. That should be into around 1.6 as well. Yeah. So the period of the square function is half the period of the regular function. And on the top of that, we have only positive values, no negative values whatsoever. Okay. So going from 0 to 1200. Okay. Note, see that the average is going to be right in here, half of the peak of the square of the function. Okay? That's how we visualize it. You know, half of the maximum value is going to be the average of the square of this function. So notice for the above graph that, right, is equal to 0. However, if we plot the square of the function, we get non-zero values, or like this one here. Let's snip again. V squared versus t. Okay. Taking the average, of the above functions, we get the following. Here you go. Half of the peak value. We get half of the peak value. This one is a constant, right? Average of a constant is going to be the constant itself. And now we are left with the average of the sine square, which is going to be half. That's how we find the average of the square. So that's most of the work done. Half of the peak value. And now we are left with taking the square root of the average of the square. Finally, we take the square root of the above to ensure we end up with the right units, the correct units. Okay. So here we go. And then we call this new average the root mean square value. RMS, root mean square value. And now my new average is going to be the peak value of the voltage divided by the square root. Square root of 2, divided by the square root of 2. We get the same thing for the current. We get the same thing for the current. We get the same thing for the current. Okay, so here we go. Root mean square value. Root mean square value. And now we gotta apply that to the power. Because power is VI, root mean square value of the power is going to be the root mean square value of the voltage times the root mean square value of the current, RMS. Okay. V naught over square root of 2, I naught over square root of 2, V naught over I naught, V naught times I naught over 2. Okay. And this is the type of measurement that we get with our multimeter. Okay. And now we completed everything that I wanted to cover in chapter 23, including that section 20 that we skipped, right? Here you go. We did all of that here, alternating circuit with the resistance R, capacitor and capacitive reactance, inductive reactance, the RLC circuit. Let's take a look if we are missing anything else. That's chapter 23, right in here. Capacitor inductors. Those two chapters, the last two chapters, we are going to skip it, okay? Resonance in electric circuit. I want to see this one here. If we missed anything. Series. Yeah, here's the power. Let's see here. Series combination. Let's see once. Yeah, let's see here. We are over now. Yes, skills. Example 4. But yeah, we're skipping this one right in here. What about let's do the power of RLC circuit too. The one that we saw is for the power of a resistor of AC circuit that has a resistor only. Okay, but when we introduce the other elements, the capacitor, right, and the inductor, then things change a little bit. Okay, and okay, here you go. The phase angle is important because it has a major effect on the average power delivered to the circuit. Okay, remember that on the average, only the resistance consumes power. Okay, and according to figure 23.11, let's see, 23.11. This one here. Figure 23.11. Cosine of phi is VR over V naught. okay, which is, IR, right? And IRMS times R, IRMS times Z, times Z, right? Or, R over Z, so that the resistance is Z cosine of phi. Okay, so let's do that. Let's Okay. The above equation applies to an AC circuit that has only a resistor. However, in a RLC circuit, things change a little bit. Okay? Things change a little bit. Looking at the let me copy and paste the figure here. Looking here at this figure, looking at the last figure, no, it's not the last figure. Looking at the figure below, looking at the figure below, looking at the above figure, let's put an above figure. We have the following. That's the figure we are referring to. Okay. Here's the phi angle. Okay. V of the resistor divided by that's what he called the V naught, right? Or the VRLC, which is equal to the V naught, must be cosine of theta. So let's hear. We have the following. Cosine of theta, no, cosine of phi. Cosine of phi. Here you go. Cosine of phi is going to be V sub R over VRLC, okay? And this V he called the V naught. This V sub R is R times the current. And let's call that the RMS current. This one here is going to be zeta times RMS. Okay. This is actually what we have right here. Okay. So we go ahead and cancel the IRMS. This IRMS is canceled out. We end up with this value, and we can even here write the resistance as being zeta cosine of phi. Cosine of phi. And now we can substitute that into the equation for the power. Okay? Ri square. Ri square. Here you go. The equation of the power becomes, P equal to Ri. Equal to Ri. No, it's not Ri, is it? Yeah, that's Ri. No, V go to Ri. Ri square, okay? Ri square. right? Ri square. And then we can here write in terms of the root mean square. What is root mean square? Is the I, like that. The resistor doesn't change. The resistor is a constant. For a given resistor, for a given element, the resistance is constant. And now we can use the relation between the resistor and the zeta, right? That's what I'm going to put it right in here. And you can see that the depends on the phase angle difference, okay? Here, the root mean square value, right, of is going to be I naught over 2. Let's see if he put I naught over 2. No, he didn't put I naught over 2 here, but that's I naught over 2, okay? And the z, remember what the z is? The z is that the square root that you saw before, right? Here you go, square, and we have r square. And here we have chi L minus chi C, like that. Cosine of phi. Let me put cosine of phi at the end here. If phi is 90 degrees, the power is going to be 0. If phi is 0 degrees, right? Then we have only the resistor in the circuit. And now we are done. Now we are done. And now we can start chapter 24. What time is that? I think we can have a break now, right? Let's have a break now. And then we go until it's 11:40 right now. Let's take a break now. And then we start chapter 24, which is electromagnetic waves. Break. 11:40 to 11:55 a.m. Did I miss any questions from you? Okay, so I see you in the next 15 minutes. Okay, now let's go back here to the book. Now we're going to look at electromagnetic waves. Okay, yeah, that's a very important chapter because that's how telecommunications started. Your cell phone uses electromagnetic waves to communicate, for us to communicate with each other. Okay. And electromagnetic waves rely heavily on the equations of electricity and magnetism. Let's write that down. Electromagnetic waves. And let's like that. So it's very difficult, extremely difficult to emphasize the importance of this material in the understanding of electromagnetic waves. And this whole thing that we're teaching is the very foundation of our modern society. Okay, without this knowledge, we wouldn't be able to have electric circuit, electric light, electricity, telecommunications, etc. Just imagine living in a world without electricity. We cannot do it without it nowadays, right? And what else is important about those equations, right? For instance, without this understanding, we wouldn't ever be able to build an electric motor and wouldn't be able to have electric cars. And without the understanding of magnetic force, we couldn't have the cathode ray tubes that were initially used, right, in the early TV and computer displays. We wouldn't be able to generate AC current. Without the understanding of electromagnetic induction, we wouldn't be able to generate AC current. We wouldn't be able to produce electricity in large scale. And it's also because of electromagnetic induction that we can create electromagnetic waves. And because of electromagnetic waves that we today have long distance wireless communication. In other words, our cell phones wouldn't be possible without electromagnetic waves, which is the consequence of electromagnetic induction. And everything goes back to the laws of electricity and magnetism. Let's spell them out here. Gauss' law of electricity. Remember, you gotta memorize those laws. I usually like to tell my students that if you have to memorize anything in physics, memorize the laws of physics until your very last day. Here you go, Gauss's law. The flux of the electric field is equal to the charge enclosed by a given, and here we should put something else. We should put we should put a closed surface here. Let's see. Yeah, here you go. Closed surface. Closed surface. We must have this, right? Is equal to the charge enclosed by the surface divided by the epsilon naught. We have Gauss's law of magnetism. We have the magnetic counterpart of this Coulomb law. Note, see that the only difference between this term here and this term is the field, right? And we still have a closed surface here. Change the E by the B. Ampere's law. And then we have Faraday's law of electromagnetic induction. Okay, what was discovered at the middle of the 1900s, 1800s? Okay, in the middle of the 1800s, in the middle of the 1800s, scientists were looking at these equations, at these four equations, and they noticed that there was something missing in one of them. Okay, let's start. Let's start with the. And there is something else that I want to tell you about this one. So there is, in the middle of the scientists were looking at at Ampere's law, and they noticed that there was something missing about it. Okay. Okay, before let's see. I don't want to talk about Ampere's law yet. Let us talk first about. We're going to talk about Ampere's law eventually, but let's concentrate on Faraday's law. Let's talk about. Let's talk first about Faraday's law. Okay. Something that I didn't mention to you. Mm-hmm. The first thing that I told you is that the first thing that I told you was that a change in flux, magnetic flux, in B flux, induces an electric potential difference, which powers an induced current. Induced current. That's what I told you. However, there is far more to this law than what I have told. You. I have told you. Okay. In reality, a changing in B flux not only induces an electric potential difference, but even better, it actually induces an electric field in space. Okay? That's remember, okay, the electric field is related to the electric potential. So that's what scientists realized at the time. First, they start doing experiments with wires, and they saw that when they change the magnetic flux, you can measure the electric potential difference in that circuit. But then they start continue thinking about it, and they said that there was something far more basic than the electric potential difference. There was something else that is the electric field, an electric field that was giving rise to this electric potential difference. Okay? Keep that in mind. So you didn't need, you did not need an electric circuit, an electric conductor, right? Let's put that an electric conductor to generate. We do not need an electric conductor for this law to take effect. If somewhere, if you were to change the B flux in a region in space, comma, this B flux would automatically induce an electric field in space. Okay? So now we can here write our law, our Faraday law, in a different way. Okay? We can add a new term that is related to the electric field, and that's the one that I'm talking about. Okay? So here you go. If R times induced current is equal to V induced, right? V induced should be also be equal to this summation that you see right in here, where this term here is the electric field. And I'm going to here write that in terms of the change in magnetic flux. I'm going to illustrate that. Let me close this one now. Okay, electromagnetic waves. So here you go. The story that I initially told you was the following, right? You need a conducting wire to have you need a conducting wire and a magnetic field that change in time to measure an electric potential difference that was induced. Okay, so here you go. B changes in time. If dB dt, if delta B, delta T, let's put delta B, delta T, is greater than 0, symbol. Why? It's just not changing. Oh boy. Huh, strange. Okay, oh, why it's not changing? I do not know why. I think I know why. Okay. Yeah, okay, that's the problem. I was using the wrong keystrokes. Okay. If delta B, delta T is greater than 0, then you must have a current that's flowing in the counterclockwise direction. Okay? To cancel the increase in the magnetic flux here inside. But there is far more to that than the magnetic, the electric potential difference, in the induced electric potential difference. Okay, what we also have, which is actually far more fundamental than the electric potential difference, is an induced electric field that circulates about this around this region right in here. Okay, and it is this electric field that's powering the current in this conductor. If we decrease the size of the loop, the electric field would decrease as well. Okay, and notice that I didn't put the conductor. I took out the conductor from this region. I just put a dashed line here to show to you that the induced electric field does not require a conductor. The conductor is right there only to help us our measurement, and to help us making a measurement. Okay, so that's one important piece of information that you have to have in mind. You do not need a conductor to induce an electric potential difference. In reality, what's happening is that a change in magnetic flux is inducing an electric field, not an electric potential difference. Okay, that's the first important lesson that you have to take home. Okay, the above equation states that a changing magnetic flux induces not a induced electric potential difference, not a potential difference, but something far more primary than that. An actual induced electric field, which will power the current in any conductor subjected to a changing magnetic flux or changing magnetic flux. Okay? Did you get this idea? Put that in, treat this idea nicely. First memorize it, and later on, if you still don't understand, just memorize it for now, and then eventually you will understand. This is a far more, what you see above is a far more generic format of the Faraday's law. I'm gonna just copy and paste what I mentioned to you before. Here you go. What you saw there in the, okay, what you saw there in the illustration, right, is going to be exactly what I'm gonna copy and paste here. You already know that a change in magnetic, okay, summarizing, right? Summarizing. One, you already know that I change in magnetic flux induces the current in a circuit. In a circuit. But in reality, what happens? Something far more interesting. In reality, what happens is an induced electric field that is powering the current and consequently giving rise to an induced electric potential difference. I illustrated the induced electric field here. You don't, and even more, you don't even need an electric conductor to have this electric field. Don't even. Here go. And here I'm removing the electric conductor. From the region in space. And we still have the electric field in there, the induced electric field in there, okay? So that's the conclusion here. So think now that we have two different types of electric field, but just one type of magnetic field. Four laws of physics, right? Four laws of physics. Two different types of electric field. An induced electric field that depends on the magnetic flux, and a regular electric field that depends only on the charge distribution. But so far, we have only one type of magnetic field, a magnetic field that depends on the current. And don't forget the other one too, that has a term equal to 0. Okay. The first type of electric and magnetic fields are the ones generated by static sources and static current, static charge and static current respectively. And by static, we mean static sources that do not depend on time. That's what I mean by static. And the static source should be the charge for the electric field and the current for the magnetic field. We call them the electrostatic field. The electrostatic field, right, obtained from the first equation, and the magnetostatic field obtained from the other equation. In the case, however, in the case of the Faraday's law, something has to change for the induced electric field to exist. In the case of Faraday's law, something has to change for the induced field to exist. If the flux doesn't change, then the induced field must be 0. Must be 0. Must be 0. Okay? So let's summarize that in a table format. We have something like that: electrostatic field, magnetostatic field, and the induced electric fields. The source of each of those fields is the electric charge for the electric field, the electric current for the magnetic field, and for the induced electric field is going to be a change in the magnetic flux. Notice that I put a force, another column right here. That's in blank. Okay. And by the way, scientists were looking at that back in the 1800s. Source behavior, static charge, static current, dynamic current. Because in order to have a change in the magnetic flux, the current must be changing. What's the behavior of those fields? Electrostatic and electrostatic, they radiate from the charge, radiate or converge, right? Radiate or converge towards the source. For the magnetostatic, it circulates around it. And for the induced electric field, you already saw that it circulates around the magnetic flux. Okay? Circulates around, let's say, around the B field. Circulates around the source. Field behavior with respect to the source. Let's put it this way: with respect to the source. radiates from the source. Circulates around the source, circulates around the source. And again, notice that we have empty cells in there. Now, we can go back to Ampere's law. Okay? Back in the mid-1800s, there was someone called James Clerk Maxwell who was looking at the equation for the equations of electricity. These four equations. These four equations of electricity and magnetism. What he realized at the time was that these empty cells here in this explanation, that's what he was looking. He thought it was odd. Why is that I induced electric field? Why is that a change in magnetic flux induced an electric field? And if you have changing magnetic flux induced an electric field, shouldn't we have a changing electric flux to induce a magnetic field? That was the question that he was asking. Okay, so those are the questions that you were looking at. So he asked himself if a changing magnetic flux, here you go, right in here, induce an electric field. Can we also have the opposite? Scientists usually think like this way. If something that's in one way, would be the reverse process true as well? So he was asking himself, would it be possible for a changing electric flux to induce a magnetic field? And the answer turned out to be a yes, a resounding yes, okay? The question is which equation would carry this information? What he found out was that the equation that was incomplete, by the way, one of the equations was incomplete, was exactly this equation right in here, Ampere's law. This equation that you see here was incomplete at the time when Maxwell was looking into it. And it was because of his discovery that today we have telecommunications, okay? We have our cell phones. And here is the term that was missing. Here is the term. Here we have the changing magnetic flux, and here we have the changing electric flux. That's the term that was missing. I'm going to put it in red color. Okay? And it's, let's put everything in the term here in red color, right? And now, with this introduction of this new term, we can explain the electromagnetic field, the electromagnetic wave. Okay, so Maxwell did discover that there was a missing term in Ampere's law. And this missing term suggested that both a changing electric and magnetic field were reinforcing each other. So if I were to let's see, if I were to if you were to visualize it, let's see if I can get that visualized. Here you go. Here you go. Here is the magnetic electrostatic, right? Electrostatic field. It radiates away, or it sinks into a negative charge, right? That's a magnetic field that circulates around the current. Okay, and this magnetic field decreases as you move away from the source. And then we have the induced electric field. The induced electric field that happens in space and circulates around the lines of magnetic field. And finally, we have the opposite. if you were, that was the discovery of Maxwell. If you change an electric field, if you change an electric field in time, you are going to induce a magnetic field. It goes both ways. And how do you do that? You can do that with the parallel plate of a capacitor. Connect the parallel plate of a capacitor to AC generator, okay? And you obtain an electric field that changes in time. I'm going to put it out without the in, okay? Electric field that changes in time and is inducing a magnetic field. Okay, so that's what that term is all about. And let's try to visualize. Here you go. Consider a generator that's initially uncharged. Okay, as time goes by, it becomes charged. The charge builds up, right? And then the charge decreases. Can you picture that? It's a circuit that oscillates in time. It's like the generator that you saw before, right? So in this generator, the current is changing as time goes by. Not just the current is changing, but the electric field also produced by this charge displacement is changing in time as well. So let's visualize the production of electromagnetic waves. That's the whole idea here. And here you go. One way to visualize an electromagnetic wave. Consider a generator. Attach it through two conductors, creating an open, attach it to a conductor, to two conductors, right? Two pieces of conductor, creating an open circuit. Here you go. Let's get this one here. That's my generator right here. This generator can be thought in terms of an electric dipole, but it can also be thought in terms of an electric magnetic dipole, because there is current flowing back and forth here. Okay. Okay, so here we go. This electric dipole antenna generates an electric field that changes in time nearby. The changing electric field induces a magnetic field, creating an electromagnetic wave that moves away from this antenna. That's what a generator is all about. It's like an antenna that can either emit electromagnetic waves or even receive electromagnetic wave. Either a transmitter or a receiver can be either one. Two different ways of visualizing this electromagnetic. The second way, I didn't mention to you yet, is if you have numbering. I hate that. I just set numbering values to. Another way would be to attach a generator to a closed loop. And let me illustrate that for you. Here you go. The closed loop is something like that. Okay, here is my circuit. Okay, it can be also be a square as well. And we have a generator that generating a current that bounces back and forth. Okay, this is called magnetic dipole antenna. The other one would be an electric dipole antenna, because we have this polarity here of the device. Both configurations generate an electromagnetic wave. And here I illustrated the electromagnetic wave of this magnetic dipole antenna. Here's the electric field. And let's see. Yeah, here's the magnetic field, and this one here's the electric field. Magnetic field and electric field. And they are perpendicular to each other, okay? If you're in free space. Both configurations, here writing the equations. Let's take a look at simulation that we have in the internet. Simulation of electromagnetic wave. Simulation of an electromagnetic wave. Let's take a look there. We have 15 more minutes to go. Okay, so here we go. Okay, right in here. See, whatever is in red is the electric field. Whatever is in blue is the magnetic field. Here he doesn't show us the source. He doesn't, but you can think of that in terms of an electric dipole somewhere. Okay, that's generating this electromagnetic wave. And the electromagnetic wave is made up of electric and magnetic field. They are perpendicular to each other. But we can produce an electromagnetic wave only when the electric and magnetic field change in time. We can derive the wave equation that you saw before in physics 6, right? From the equations of electricity and magnetism. Here you go. And the way we do is like that. We write the equations. We realize that very far away from the source, that is from the source, let's say from the generator, we have no charge distribution and no current distribution, which results in the following set of equations. Okay, so here we go. The current, the enclosed current is going to be 0. The enclosed charge is going to be 0. I'm talking about in this point here in space, okay? In this point here in space, there is no electric charge, no electric current. The current is restricted to the point where the source is located. So this term here becomes 0. This term also becomes 0, far away from the source. Okay, and so what you end up seeing right in here in those two equations, the last two equations, when combined, to the wave equation. We're not going to do that here because it requires advanced calculus. Okay. With the travel with a velocity given given by one divided by square root epsilon naught mu naught, which is 300,000 kilometers per second. That's what Maxwell found at that time, okay? And we can come up with some simple examples. Oh, and by the way, what are the types of electromagnetic waves? Okay, what are the types of electromagnetic waves? Okay. And also, how can you generate? You already saw how you can generate, but there are other ways too, right? What are the type of electromagnetic waves? Which other way can we? Which other way can we generate an electromagnetic wave? Wave. Okay. Let's put this question first. Okay. We can use an RLC circuit. To generate these waves. Okay, and what are the type of electromagnetic waves? A given electromagnetic wave depends on the frequency of this circuit of your RLC circuit. Okay? And let me list all the types of electromagnetic waves we have out there. And okay, of your a given electromagnetic wave depends on the frequency F of your RLC circuit. Okay. Furthermore, we can also change the frequency and wavelength of the wave by adjusting the capacitance and inductance of the circuit. The resistance does not affect the wavelength of the circuit, only the intensity of the signal. The wavelength and frequency of the circuit affect which type of electromagnetic wave we have. Which type, and we have the following waves, okay? Electromagnetic waves. The first one is the radio wave. Okay, and if you build a circuit that the current has a frequency of up to 30 megahertz, you can produce a radio wave. Think about that. 30 megahertz is 30 million hertz. So the circuit is bouncing back and forth 30 million times in a single second. And above the radio waves, we have a microwave. Microwave, part of the electromagnetic spectrum. 8 more minutes to go. You don't, okay, here you go. That's the region. And that's the region your microwave oven works. Find out its frequency of operation. They usually imprinted that in the back of the microwave that we have at home. In addition to radio waves and microwaves, we also have infrared radiation. And all that thing can be produced by having the appropriate circuit, by having an appropriate circuit, a circuit in which the charges are bouncing back and forth in the circuit. We also have visible wave, visible radiation, visible region of the spectrum, of the electromagnetic spectrum. That's our eyes are sensitive to. Our eyes cannot see infrared radiation, cannot see microwaves, cannot see radio waves. You need a special device to detect them. The next region in the spectrum is the ultraviolet wave. Then you have X-rays and gamma rays. Okay. Terahertz. I believe it's pentahertz here. I believe this one is ecohertz. So let's see. Pentahertz. Peta. It's not penta, it's peta. Petahertz. Okay. 10 to the 15. And then let's see, petahertz to hertz. Let's see here. The other one should be ecohertz. Let me take a look. Exa must be exahertz. Yeah, exahertz, e to 10 to the 18 hertz. Okay, what's the type of thing or problem that you might see in the exam, right? Just remember, 5 more minutes to go. Just remember the theory of waves, the wave theory. Wave theory, okay? Some of the things that you have to remember is the relationship between wavelengths, period, and period of a wave with respect to its velocity. Remember that? Okay, remember the velocity of a wave, right, is going to be distance divided by time, right? Distance divided by time. Here you go, velocity of a wave. Oh. Velocity of wave should be distance. It's not difficult to memorize that, right? Divided by time. What is distance and what is time of a wave? In a wave, right? What is related to distance and what is related to time? Distance of wave is related by the wavelengths of the wave. And in the case of time, we should use the period of the wave, t, lambda over t. By the way, the inverse of the period is the frequency of the wave. That's another way of writing the speed of a wave. In the case of an electromagnetic wave, its speed is represented by the letter C, or lambda f, 300,000 kilometers per second. And now we can, for instance, find out the wavelengths. What time is that? 3 more minutes to go. Let's do a quick example. Find the wavelength of an electromagnetic wave that has this frequency, 750 terahertz. You have to know what tera is all about, right? Let's see. Let's go here, terahertz. Terahertz to hertz. Yeah, 10 to the 12. Okay? And the solution should be find the wavelength of an electromagnetic wave. Here's the equation for the electromagnetic wave. We have the frequency. We have the speed. We want to find out, the wavelengths. Theta is what? Again, 10 to the 12, right? Yeah, 10 to the 12. 750 times, there you go. One more minute to go. Times 10 to the 12 hertz. Don't forget to put the units. Then we go ahead and you solve for lambda. I have all the derivation here, right? Let me show that we are running out of time. Okay, here you go. It's 0.4 microns. 0.4 microns is 400 nanometers. That correspond to wavelengths of the red light. This correspond to the wavelengths. No, of the blue light, okay? These correspond, oh gosh. 400 nanometers. I erased something that shouldn't have erased. Okay, nanometers. That correspond to the wavelengths of the blue light. Of the blue light. Okay, so we can stop now. It's 12:50. Do you have any questions? Someone left asking me a question, right? Stefan, at the end of the class, can I ask you a question? Okay, yeah.
Professor, I have a question about lab 3. So on one of the DMM resistors, it requires for the it requires for the value to be minimum 1, but for mine the value is 0.001. How many significant figures do I put for that value?
Let me see. What's your group number?
Group number 7.
Group number 7. Let's go there.
Table 4.4. 4-4.
Lab. Group number 7, right? Group lab number 3. Group number 7.
Yep.
Let's take a look here. Okay, which table is that again?
4-4.
Okay, that's the table. Okay, don't forget is the inverse, right? I'm taking the inverse here.
Yeah.
Did you plot this graph here? You have to plot this graph.
Yes, I finished the entire lab. It's just those the DMM value, not the first one, but the right one. That one.
Yeah. Okay, well, what do you do? First, you gotta look at. You're asking the significant figures, right?
Correct.
Stefan?
Yes.
Okay.
Yeah.
First, you gotta look at this number here, right? At this column. Look at this column first.
Okay.
Or look at this because that's the actual measurement. This is not an actual measurement. This is the inverse of the measurement. See that?
Okay.
So you gotta look at this one here. Let's take a look at this one first. 9590. 9590, right?
Yes.
So let's take a look now at that table that you have for the significant figures.
It should be 4. It should be 4.
Yeah, it should be 4. Okay. Yeah. Let me just double check, okay? Make sure.
Of course, yes.
Let's see. Here, right in here. That I want to take it out. Hopefully, that's the table here. That's the table. 9,500, right? 9,500, whatever. Okay, so you gotta look at the resistance. Oh, that's the first table, right? You look at this table, right?
Yeah.
Okay, 9,500 is between those two values, right? And just
Mhm.
like you said, there's four significant figures, right?
Yeah.
So how do you write that down? You write that down, here you go. Right click, format cell, number, zero decimal places because you have four significant figures here, right? That's the right way of writing down.
Also, a quick question for, let's say, 9590. That's
Uh-huh.
only three significant figures.
Actually, it's four. Zero here onto the right side is considered a significant figure.
Oh, really? Oh,
Yeah, zero to the left is not, okay? The extreme zero to the left is not, but the zero to the right or in between significant figures is considered a significant figure.
okay. I
Okay.
see. Okay.
Okay, so
Yeah.
if you have four significant digits here, you must have four here as well. Okay.
Oh, okay. I see. But the value for that one to the right is really, really low. So it's fine
Yeah,
if I put a lot of decimal places.
yeah, that's right. Here you go. One way to do that. Here you go. Format cell. Let's see here. So if you want to keep it scientific, you have to add three decimal places, right? Now you have four significant figures. That's one way. Another way to display it is to put it in numeric format. And then you're gonna have to, play with it, right? How many? Okay, here we have one significant figure. Four decimal places, one significant figure. Five decimal places, two significant figures, right? And so on.
Yes. Yeah,
Okay.
I get it. Yeah.
It's
Uh,
preferable for a number small like that. It's preferable if you put it in scientific format.
okay. For some of them, I didn't know that zero was considered a significant figure.
Oh
Is it
yeah, it
fine
is.
if I put that one in scientific notation correctly, or should I change it to numerical?
Oh, it's up to you. You can even display like that, right? Or
Yeah.
you can also display like that as well. Here goes scientific format, right? Now you have to
Mhm.
put three decimal places.
Yeah.
Okay, 9.590.
I
Oh,
see. Yeah. Okay, one last question. For the nominal values of that table, in
uh-huh.
the inverse, do we do it like that, how you just showed me? Because I just plotted the significant figures. Was I supposed to look at it as something else?
Okay, for this one, you have to display also the significant figures, right?
Yes,
And because it's the nominal value, how many significant figures the nominal value of the resistance must have?
it should be two.
Yeah, should be two. So the inverse of the nominal value should be two as well, right? There you
Yeah.
go.
Oh, I
Format
see. Yeah.
format cell.
Hmm.
Let's do scientific, right?
Yeah.
All you gotta do is to add one decimal place.
Okay. And for values that have a lot of decimal places, it's preferred to be in scientific.
Yeah. If you have lots of
Perfect.
decimal places, put that in scientific format.
Okay, perfect. I understand it. Thank you so much.
Welcome.
Thank you.
Oh.
Hello, Professor. Can you hear me?
Yeah, I can hear you.
Okay, that's great. I kind of need help looking over my lab 3.
Lab 3, did you upload it?
Yes.
Okay, let's go.
No,
Oh, you didn't upload it?
because I'm still trying to figure out the significant figures and if my graphs are correct. I
Okay.
feel like they're a bit off.
Uh-huh.
I can
Okay,
screen share.
which group number are you?
I am group number 4.
Four. Group number, lab number 3, group number 4, right?
Yes.
Lab number 3, group number 4. Okay, so which table do you want to cover?
Can we cover the first table?
First table, this one right here,
Yes.
right?
Yes.
Okay. So the You gotta concentrate on those. You start with this column here, okay? That's for the nominal value. That's the color code, right?
Yeah.
Color code. So the color code, for the color code, you have only two significant digits because it's the two colored bands. The two colored bands are the significant digits of the resistor, okay?
Alrighty.
Okay, so all you gotta do is to display two significant digits here. So that should be scientific. If you do just one decimal place, you will be able to display two significant digits, okay?
Alrighty.
And here is the same thing, right? Everything here should be two significant digits.
Okay. Yeah, I have that down.
Okay. What about here for the multimeter? Did you do that for the multimeter as well?
Yes.
Okay, so you have no problem here, right?
No.
Okay, so you gotta use.
I'm just unsure if I have it correct.
Okay,
Like,
okay.
I've done the charts and I did majority of the sig fix, but my charts are looking a little off, or I'm not sure if they're correct.
Oh, your chart. Let's see. Let's see if your chart looks just like mine, huh? I'm gonna plot it. The first chart, you mean?
Yes.
Okay, let's take a look at the first chart, how it looks like. Okay, does it look like that?
Yes.
Okay, so you got it right? Click, right
Looks like
click.
that.
Looks like that. Okay. And then you have, what is the slope in your chart?
My slope is 1.0518
Okay.
x minus 1.3951.
Okay, you got it right. There's no problem about, okay.
Alrighty. And my R value was 0.9995.
Okay, 9995 is exactly. So you got it right.
Could we check the second chart?
Okay, let's check the second chart. The second chart is those two, okay? Resistors in series. Insert, chart, here you go. Did you get that one too, like that?
Yes.
Okay, add trend line, display R square, right? Here you go. So looks like you got it right, huh? 1.0156 for the slope, right?
Yes.
Okay. You want to see the other one?
Yes, please. Because I was comparing charts and comparing the tables with my lab partner, and we got different answers. So that's why I'm double checking mine.
You mean you compared that to your group, to the member of your group?
My group member, yes.
She got it different.
Yes.
Yeah, I gotta see what's different, right? Did you get this chart like that? A bunch of points here and just one lonely one right in here.
Could you show me the highlighted points again? Or like which columns you highlighted for the third chart?
Yeah. Okay, here you go. This one and the nominal value.
Oh, okay. For my third chart, it's different. But
F and I.
I thought it was okay. So which ones are highlighted for the third one?
Yeah, it's I-59 through I-63, right? And F-59 through F-63.
Alrighty. Huh. Hold on. My chart is looking weird.
Do you want to share your screen with me?
Yes. One moment.
Let's see. Share settings. Let's see. Post tools for share. Post only, you can share all participants. Okay, I'm gonna stop sharing. You share your screen with me. Oh, let me turn off my stop recording.